Welcome to our training module covering another member of bearings in the sliding contact bearing family, the Kingsbury thrust bearing. In this segment of our course, we will introduce you to thrust, the force in rotating assemblies that required man to invent the thrust bearings. We will also define a few terms peculiar to thrust bearings and give a brief historical sketch of the Kingsbury thrust bearing. Whereas sleeve bearings are designed to carry the radial loads of a rotating element within a machine. Other forces acting on the rotating element and axially with the shaft are frequently present. This force is the cumulative effect of gas or liquid pressure acting on elements of the rotating assembly. These thrust forces tend to move the rotating element in the direction of the force. The position of the rotating shaft within the machine must be maintained by thrust bearings exerting an equal but opposite force upon a thrust collar locked to the shaft. In machines with vertical shafting, axial loads more or less are always encountered and are usually in one direction only. In addition to forces caused by liquid and gas pressures, the weight of the rotating assembly itself must be supported. In machines with horizontal shafting, axial loads may or may not be encountered. Horizontal motors, such as the one shown here, produce no thrust load as they are magnetically centered during normal operation. But heavy horizontal thrust loads are encountered on centrifugal compressors like this one. Large axial thrust loads also occur in the larger steam turbines, and they too must be equipped with thrust bearings. In some pumps, as is the case with this one shown here, the horizontal forces are such that a thrust bearing is required to equalize these forces. Gearboxes, which sometimes are designed to produce no horizontal thrust of their own, may require thrust bearings to resist thrust imposed on them by the machines they are driving. Bearing thrust loads cannot exist in opposite directions at the same time, but we frequently find thrust appearing in one direction during the normal operations of a machine, with the thrust changing direction during startup and shutdown. Thrust bearings, then, of the type we will be discussing must be capable of equalizing thrust loads in either direction. The bearing carrying the thrust load during normal operation of the machine is the active thrust bearing. The bearing unloaded during this period of operation is known as the inactive thrust bearing. Some thrust bearings are designed to run with a thrust collar that may run in either a clockwise direction or counterclockwise. These bearings are said to be bidirectional. Other thrust bearings are unidirectional, that is, they are designed to run with a thrust collar that turns only in one direction. Horizontal shafts operating at low speeds and low axial thrust are generally supported by sleeve bearings with thrust shoulders, as is seen here. In installations where speeds are much higher and thrust loads much greater, bearings of Kingsbury type are generally employed. In earlier times, axial shaft thrust was absorbed by a system of shaft collars turning with a thrust block as shown in the graphic here. This thrust system served its purpose for many years, even though it had many limitations. Men working in this field at that time did not fully understand the theory of lubrication as well as it is known today. So he limited his design of this type of thrust bearing to thrust loadings of 50 to 75 pounds per square inch. In his designs, as thrust loads increased, his only resource was to add additional collars and longer thrust blocks. The more collars he added, the more difficult it became to get each thrust block to carry its share of thrust load, and it took a lot of horsepower just to turn the shaft. The whole thing was becoming slightly ridiculous. In 1896, Professor Albert Kingsbury applied the developing theory of lubrication to a new type of thrust bearing that bears his name, the Kingsbury tilting shoe thrust bearing. His first commercial product was installed in a vertical shaft turbine in 1912 and was still running 40 years later. The Kingsbury thrust bearing eliminated or reduced many of the limitations that were imposed by the old collar and block system. First, it permitted thrust pressures on the bearing to increase up to 20,000 pounds per square inch of projected area. Second, it permitted the use of a single thrust collar. Third, the bearing was designed to be self-aligning with each bearing face carrying its share of the load. And fourth, horsepower losses in the bearing were reduced to about 5% of the old values. The Kingsbury type bearing is generally manufactured in sizes from about 3 inches in diameter, sustaining loads of a few hundred pounds of thrust, up to bearings in excess of 100 inch in diameter for the hydroelectric generators, supporting loads up to 3 million pounds and more. You will encounter thrust bearings of other basic designs such as this tapered land thrust bearing and this thrust plate. There are variations in them all. In the next segment of this module, we'll identify the parts making up a Kingsbury thrust bearing and with lubricant tell you how it works. But first we have some questions for you in exercise number 1 of your workbook. During this segment of our course, we will take a look at a typical thrust bearing assembly, identifying the basic parts and show you how it works. We'll be using this pump only as a vehicle to help us in this presentation. The vehicle could be a turbine, a compressor, a gear reducer, or any type of machine that would employ a thrust bearing of this type. We'll be primarily concerned with this bearing housing and the bearings within. The bearing housing is split horizontally, and the lower half of the bearing housing may be considered as an integral part of the pump case. The oil pump being pointed out here is driven by the pump shaft and supplies clean, cool oil to the thrust bearing. Through piping to the oil inlet connection shown here on the side of the lower bearing housing. The upper half of the bearing case bolts to the lower half as shown here and is aligned with dowel pins. Inspection plugs on the top half of the bearing housing permit filling the oil reservoir that provides lubricant to a sleeve bearing that is compartmented with the housing. By removing the plugs, the bearing oil rings may be observed. A breather cap located here is to ensure that atmospheric pressure is maintained within the bearing housing. The oil having passed through the thrust bearing is returned to the oil reservoir through piping tapped into the oil outlet shown here. Now, having removed the upper bearing housing, we can better see the parts making up the bearings and their arrangement. As explained earlier, the bearing housing contains the pump shaft journal bearing as is being pointed out here. This bearing is of the split sleeve type. Your prior instruction should have familiarized you with this bearing and we will not deal with it here. Note that it is compartmented with the bearing housing and is lubricated with oil rings. Lubricant for the sleeve bearing is supplied by the system lubricating the thrust bearing. The thrust bearing is the assembly shown between the 2 points indicated here. The first part of the assembly that we want to identify is being pointed out here, the thrust collar. The thrust collar is a highly polished, solid metallic disc bored to slip over the pump shaft. The collar is keyed to the shaft and secured with a lock nut. The thrust collar rotates with the pump shaft. We'll take a closer look at this assembly later on. The thrust collar rotates between 2 shaft bearing assemblies being pointed out here. The thrust bearings are snugly encased in the bearing housing. The thrust bearing assemblies are not permitted to rotate by virtue of these base ring keys, which are affixed to the base ring, and engage a notch in the bearing housing as is being shown here. Thrust bearings are laterally positioned in the bearing housing, with the oil pump bracket or housing end cap being pointed out here. A static O-ring here prevents oil from leaking through the fit between the pump bracket and the bearing housing. A shim pack, as shown here, provides a means of adjusting the operating clearance required in the thrust bearing assembly. This clearance is specified by the manufacturer and allows for expansion of the bearing components due to heat and allow for a film of oil between the thrust collar and the thrust bearing during the operation. A bronze ring, as shown here, is loosely fitted in a groove in the compartment wall. The ring may move freely in a radial direction, but a dowel pin not shown prevents the ring from rotating with the shaft. The seal ring fits the shaft with very little clearance and prevents excess leakage of oil from the thrust bearing compartment and prevents air from entering the thrust bearing housing. Another bronze ring, identical with the one we just showed you, is recessed in this pump bracket and is retained by the shim pack. Its function is the same. Now, by removing the pump bracket and lifting out the thrust bearings, we are able to see the shaft adjustment shim pack. The shortening or lengthening the shim here, we are able to adjust the lateral position of the shaft to ensure that the rotating element of the machine is properly positioned in its case within limits of the adjustment. We mentioned earlier that the thrust collar was locked onto the shaft with a lock nut that we can now see here. The lock nut is then secured to the shaft with a lock screw being pointed out here. Now, let's take a look at the thrust bearings in detail as shown here. Remember, there are two thrust bearings in this assembly, one active, one inactive. In this particular case, both bearings are identical. We will only examine one of them. Do not expect all thrust bearings to look exactly like these. The bearing proper is divided into segments called shoes. This bearing has 6 shoes, as you can see. However, you may expect this number to differ in the many bearings that you will experience. The bearing face of the shoes is surfaced with a thin coating of Babbitt as shown here. In new condition, this Babbitt surface is pocked to retain a sufficient amount of lubricant to suffice during startup. The radial edges of the Babbitt surface are beveled or rounded. This beveled edge allows an easy entrance of oil into the area between the shoe and the collar, where a wedge-shaped oil film is formed. On the reverse side of the shoes, a shoe support with a pivot button is permanently recessed in the shoe. The button is slightly convex to permit the shoe to rock in any direction to self-align with the shaft collar and permit the formation of the wedge-shaped oil film. Now, after removing 3 of the thrust shoes, other components can be seen called leveling plates. The upper layer of the plates, one of which is being pointed out here, is called the upper leveling plates. The leveling plates are loosely located in the base ring with screws. Now, having removed 3 segments of the upper leveling plate, segments of the lower leveling plate can be better seen, one of which is being indicated here. The lower leveling plates are loosely positioned in the base ring with dowels. The leveling plates are levers with center fulcrums, as can be observed here in this cutaway assembly. The function of the leveling plates is to align the bearing shoes with the thrust collar and to equalize the thrust load among the thrust shoes to compensate for any slight misalignment of the shaft axis from the normal. Thus, as demonstrated here, a deflection downward of the center shoe because of too much thrust load on it will, because of the leveling pads, cause the adjacent shoes to rise upward to assume more of the thrust load. The last part of the thrust bearing that we want to identify is the base ring that provides the support for all the bearing parts and keeps the parts in their proper position. The bearing is designed into 2 basic halves, which permits radial assembly of the bearing. Now that you have seen the makeup of a thrust bearing, let's briefly describe its operation. Thrust from whatever the source is axial with the shaft and is shown in the red arrows, and the tendency of the thrust is to move the shaft in the direction of the force. This thrust is transmitted down the shaft into the thrust collar as indicated by the red arrows. Remember that the thrust collar is locked to the shaft and rotates with it. This thrust force must be resisted by an equal but opposite force in the thrust bearing shoes. Each thrust shoe assumes its equal share of the thrust load. The thrust bearing assembly with its shoes is fixed in the bearing housing and do not rotate with the shaft. Lubricating oil, as specified by the manufacturer, is force fed into the thrust bearing housing and is directed through passageways behind the thrust bearing base ring and inward along the shaft to the thrust collar. A portion of the oil flows through the base ring, lubricating and cooling these components. A very important part of the oil supply caused by the relative motion of the collar and the bearing shoes is wedged in between the bearing shoes and the rotating collar. Hence, in operation there is no metal-to-metal contact of the shoe to the collar. When properly designed, installed and lubricated, bearings of this type have been known to run 50 years. Without this tender love and care, they have been known to run satisfactorily for all of 15 seconds. The oil is then returned to an oil reservoir for subsequent reuse. The properties of an oil, primarily its viscosity, are used in the design of a bearing. When changing oil, be sure you use that specified by the manufacturer. The properties of an oil, primarily its viscosity, are used in the design of a bearing. When changing oil, be sure you use that specified by the manufacturer. Too thin an oil film may be disastrous for the bearing. Oils with too high a viscosity may produce some unwanted results, including a loss in power. That completes this segment of our course on Kingsbury thrust bearing. In our next segment, we will show you how to disassemble a bearing of this type and point out those parts requiring a close inspection. But before we do, we have some questions for you in the exercise number 2 of your workbook.